welcome to this module of our primer. And here we want to summarize our observations and our discussions with an architectural view to the calculus. So we don't want to use computing as a tool to solve problems. We want to use it like a language. And there's an ocean of literature, discussion, theories, and technical tutorials all around how computing and computing in architecture, in computer graphics, whatever. And I think this is not adequate for architecture. So what we can establish, and this our primer is doing, is we have a specific architectural perspective to that, because we want to cultivate that. We had talked about the different scale of space. Now we are in the quantum space, and we talked about that computing is a kind of medium, or a technical medium, or the instrumentation to play this new scale of space. So therefore the calculus is more like a language, or a writing of a language, to be able to articulate our architecture there. And we have to learn it like a language. First thing. And the second thing, we don't have to, I think it's dangerous to organize and orientate yourself in the horizontal with all these talkings around. It's very important because it's so generic with computing and so powerful that we organize ourselves vertical within the symmetries of our ancestors. And there we said we experience in our written cultural heritage three scales of space development, and this had been today with the quantum space. Then we had the space in Renaissance, with this on the scale of time, I would say, and we had it with Antique and with Vitruvius, with the scale of, I would say, space, emancipate space from things. So we discussed all this. So in these symmetries, I think we can get a clear architectural stand to look at what computing is. So therefore, let's look how our ancestors did that in a comparable in a situation. So we introduced the gnomon as a tool to enter a new and to play a new scale of space. So we had this, we have the shadow, we have the line of shadows, and we have the covering area, which is characteristic for this point in space on our planet. So we have the scenographia, which is the last memory of the last day, we called it. This is autographia. We have the ichnographia, the shadow, which is the dream of the last night. And we have the scenographia, which is the talks of today. So especially we said this is the last day, so this is the scale of space of the last day. This is of Alberti, and today it's a quantum space, it's here. And we qualify this as a space of the complex numbers. That are the dreams of the last night. So at this point, this is what the module in architecture did. Of the module, the zero-dimensional point where we are able to go up to first, second, and third dimensions. This is what we did in architecture with Alberti. The module, the column, the wall, and the roof. To do that, this point, all time. So, yeah, and with that you can go up and and go up to the next scale of architecture and organize that and bring that into a proper proportion and get known of it. So the idea of that is, or the symmetry of that is that this in computing in the lambda calculus is a symbol. And as the gnomon is the one who knows, the symbols can be anything. Not everything, anything. Anything means anything what happens, what you can think of. So things are in future as well. So technically, I can show you how this works. For example, A is a symbol. You can write any name. So, and we assign a 3 to it. So if we evaluate that, I'm doing it now here with a notebook to be faster. All this is working on the cloud. So now I'm asking what is A, and then it's the number 3. I can assign a string, so it's a list of characters, a writing to it, and then it's not a number, but it's the writing. Or it can be a book. That's all Hamlet. And if I now ask what is A, and then it's Hamlet. Or I can say it's a graphics, and then A is a graphics. I can have a model, and then A is a model. I can go and say it should be an image, then A is an image. A URL, a texture, a satellite photo, a sound. Go for a sound, play the sound. So it can be a geographics, a map. Then A is a map at a certain location where I currently am. Or when we go to it, A can be a function. So this is a pure function. Whatever there is, add 1. Whatever there is, take this and add 1. So if this is here, then I can say apply 1 to A, and then it's 2. Or I can apply, B can be a list of elements, which can be anything what we have here. And now I can apply all elements. I can map. No. I can map all elements of B to A. And then I add 1 to each element. So this is how it works. So a symbol can be anything. How is it done technically? That's the second chapter. So let's, and I would say again, we have the orthographia, we have the ichnographia, we have the scenographia. So let's have a look that everything gets, whatever you do, is a sequence of bits. For example, take a picture, or take a picture, or we can go, for example, here. Like this a little bigger. So, for example, we have an A. Then an A, the letter A is a number 97, and now I can say integer bits of this here, 2, and then you get the bits of the character A. So, therefore, for example, if we go here and say it's a character That's this is a sample text. These are the characters. Go for the character code of each character. Get the bits. Unfortunately, here the preceding zeros are cut, so we have to fill this with the pad left. Now we have the bytes of each character following the ASCII code. ASCII, you can look it up. And then, yeah, we can, this unfolding. So put that to bits, it's on a specific line. And then we can do just the same around. From these bits here, make the characters, the character numbers, and from the numbers, do the text. And the same here with an image. So we have an image, a grayscale. For simplification, we binarize this symbol. We get, this is size of the image, 125 by 90. So now we get the bits, all the lines, 100, so all the bits. We can, this is interesting, now we have the first line as a list, and the whole image is a list of lists. Always like that. So if we go here and make it smaller, we see the images of zeros and ones. So, but I go here for flatband to make a sequence without line cuts. So this is the image as bits. It's a pattern in memory. It's dead. And then you fold it back, you partition it, this data, these O's and 1's, partition it to 120 and make an image of it. And then you're back with the image. So whatever you're doing, so it can be anything, anything is unfolded to bits, and then this process of unfolding is a key to get this data back to reality. So therefore, the data is dead. So it's on the scenograph here. This is the data. These are the bits, and this is a folding, unfolding. So this is data, and this is processing. This is a process on the CPU. Scenograph here, ethnograph here, and this is the code. So we can say today, this is big data, and this is AI, the generic code. So we call this the last day. This is the last night. Dreams of the last night, memory of the last day, and this is the talks of today. This is in the trivium, tragedy. This is satire, and this is comedy. Good, but in terms of data and certain formats, folding, unfolding, we have a symbol. I would say if we put the symbol here, or the difference of symbols here, if we go, you see these are the clouds, how to stage these things, these are the friends of conceptions, these are the characters, shares, and these are the numbers. So by that we have this triangle. And now we want to, writing, so characters, data, the processors, numbers, the calculation, and then you symbolize it to the new scale. So characters are always of the last day, this is always on the last night, and with these two you have to bring that in proportion with code to make a talk today. And this is always a little complicated, and you need some humor to face these things. This is what we learn, how the principal setup always had been. Good. But these two are important in our on the next level in computation. So let's go here. Okay, now we want to go for have a focus on how numbers unfold, and we call that the stereographic projection. So we started with the point, with the position, with the unit of all angles, which means with the subjectivity of space, and we had that at the bounds. So, and we said if we want to expand that, we have the problem of branching. The principal problem of branching. So, and we, in architecture, we have that here with the bounds. This is a lineament. And this is the ornament. We have that in time, this in space. We call this here construction. Or structure. And we, in contrast here, we have a form or a figure. So it's important to see that this is with the eyes of time. So because the bounds can't be seen. So if you look with the eyes of time towards time itself, we had it with the engineering and with the graphical statics. Then you are with the shapes, with diagrams, or with a gestalt. And they are always at the end of time, toward the end of time. So if you are at a certain point in time in space, then you're looking with the eyes of time towards space. So there's another difference. Then here we talk about proportions. Here about harmony. So, and therefore proportions harmonic and harmony are proportional. So this, having these set up, here there are the numbers. And here there are characters. So the principal problem with the numbers is branching, and we call that combinatoric explosion. And I want to show how this works. Give it here and illustrate that. So in Mathematica, you have this set of functions around number theory, and here we use this function called permutation. So it's a combination of red and green, and you say, what are the different combinations of them? So then there's the red and the green and the red. So if you put a blue, then you already have not 2 but 6 combinations how to put them and permute them. If you have a yellow, then it's even more. Magenta. It's a lot to do, huh? And it explodes. So if we have, for example, now thick, because it takes too long to render that, then we ask how many are there. So you see the permutation is not fast, but then we are with 77. So it's cyan, we can have a white. Then you see it explodes. Okay, here. Black, 40,000 already. So if we have 120, look at this. Bam, this number. Unbelievable. So this is combinatoric explosion. And this is the problem of the of branching. So you see, it's 1, you have 2, then you get the next step of decisions, it's a 2-fold, then the next, and to get the circle right, it's even if you only take 120 different steps, it's this number of different points you have to go. So that's the combinatoric explosion. And the key problem with that, we had it with the circle and the line. The circle is discrete. You see, these are discrete points here. Therefore, a line can't meet a circle, because a circle is on the bounds and the line is with the branching, and they don't meet. We see that as and it's called combinatoric explosion, and this is what computer scientists or the computer technology fights with on a very basic level. And that's a problem of the numbers and a problem of the folding, unfolding directly. You see that with the branching. In mathematics it's branching, and it's the ichnographia with us. So the problem is, you're always correct, but you're not complete. You're not complete. You never get perfection. So all analysis, always on at night, all analysis, all optimization, all simulation is and fights first with combinatoric explosion, and that with the principal setup, with all systems work with like that. All structures are correct, but they're not adequate, not good enough for the real world. So, and it's real. Very important as well. All reality fights with that. So, on the other side with the characters, just the other way around. So they call it the framing problem. So it's not correct, but complete. And that's what happens with writing. So I can show you it here because I don't. So for example, if 24 characters be able to do anything in writing. So therefore I put an A, and it's the whole word, it can be anything. Then I put an R, and then you see two planets, and they start to communicate. So, and then I put an T, and then there's art. I can do whatever I like. Cluck, cluck, it's there. So I can put a N T, and then there's an art, a small thing. So therefore, it's complete. It covers the whole world. It's anything. Here it's everything, anything. But it's never correct. You never know what is there in precision. But it's complete. So here you fight with infinity toward the end of time. Here with a paradox that you can talk about anything, but it's without any sense. It's not there. So here you fight with infinity, here you fight with the paradox. So we said if we are with complete, and here this is with Gödel. Yeah, with this about the calculability. So it can't be complete and correct. This is what about the limits of computation and so on, all about. So therefore we said, this is what AI is. AI is on the ichnographia, the folding, it's a night. So you're always correct, that's AI, but you never can talk about the new day. Very simple. And it's always like that. Therefore you need the characters. And the characters, like we see it here, they have all AI enclosed, and they're all not this, because they're characters, like here. And they need to be constituted as characters or as space. So this is the theorems of Gödel dealing with these things on the mathematical level. Or with Kohlhaas, junk space. My paraphrasation is, you can't improve by doing better. So to put that to our conceptions, this is engineering, this is architecture, and I would say, to make a clear distinction, this is design, because it's about interface, and it's about optimization, it's about production, all these things of reality at night. And this is the ratio at day. So this is engineering design, this is architecture. So we are with the characters. Therefore, interestingly, the perspective drawing is a writing with characters. It's talking about buildings. So, or we had it here, for example, what we experience here. If you go to the end of time here, we had it with engineering. This is white noise. Or it's entropy. So this is at the end of time. It's a turning point where you put where you put these things at the end of time, and then you switch to the paradigm, the primacy of space. This is white noise, the thermal depth. So then here you come back with neg entropy. I'm so complicated to write by hand if you're used with computer. Entropy, I think it's just this. So this is a dispersion, so it goes out, dispersion. And this is a condensation. So it just collides in one point, not explosion at night. So this is negentropy. And with Shannon, you can look it up. Communication. The technical of communication. The basic paper of communication, I will give you the link. This is, they need white noise to condensate the bits, to be able to understand, to identify the bits in front of it with calculation. So that's the paper about what communication is about. So communication is always about, so here it's learning. Here it's about talking. And the technical thing is communication. And it's negentropic. So it's on the at the day, in the condensation process. And in architecture, I would say white noise, I would say all this scheme of communication and so on is a white wall of the international style. This would be my provocation in this context of talking.